Hi.
Hi.
Welcome to the Queen's Observatory Open House. I'm glad to see all of you out here. This is a pretty big night. So before we begin our talk session, which then leads on to going to the stations and the observatory, before we begin those, we have a few science announcements, starting with the Royal Astronautical Society and Susan. Here you go.
Hi. So the Royal Astronomical Society, the Kingston Center, we're holding a fundraising raffle, and thanks to all of the people who come to the open house and all of the fabulous graduate students who have been participating, buying tickets, we have now paid for the prize. So now we're actually reaching the fundraising portion, which happens to be a very small part of the lottery. So the tickets are going to be on sale tonight up on the deck. I'll be on the observing deck outside. We're going to be doing a little telescope demo out there. And they are $2 each or 3 for $5. And the prize is a pair of 20 by 80 binoculars, which is a sizable set of binoculars with a very tall tripod, so you can actually look at something in the sky without breaking your back. And a planisphere, which is a more sophisticated version of the little cardboard star wheels that we hand out here. Also 3 books for observing. The Terence Dickinson copy, the most recent edition of Night Watch, a fabulous atlas called the Jumbo Pocket Sky Atlas, which is a really nice scale, very easy on the eyes, and a 3rd book, which is, can't remember. Anyway, so the value of the prize is actually $600, and so we've hit the $600 mark, and now we're going to really make some money. We don't have that many tickets left, but please participate. And the draw, of course, is open to faculty as well, should they care to get in on it.
Thank you. We also have some announcements from the McDonald Institute by Ben. So he's just going to tell you a little bit about some science outreach activities coming up soon.
Thank you very much, Connor. So hey, I'm Ben. I'm the lead outreach specialist for the McDonald Institute, whatever that means. And there's some fun activities we've got running this summer. The first one here is MI Parks. So if you know somebody in high school, this is a very wonderful opportunity for them to learn how real science happens. This happens on Tuesdays and Thursdays throughout the summer. So feel free to take a look. It's by application based, but also free. Oh, sorry about that. Was there a check? Oops, look at that, much louder. Do you want me to start over? You can hear me pretty well, right? I talk pretty loud. So again, that's the MI Parks. It's for high school students, Tuesdays and Thursdays. We'll move on to the next slide here. This is a girls' camp. It's run by some of the top females in neutrino physics, astrophysics, and dark matter physics. It's going to be a 1-week camp for girls run this summer, going to grades 7, 8, and 9. So it's also free, which is a wonderful thing. And we'll go on to the next slide. This is Astronomy on Tap. Perhaps you are maybe a little too old for the previous 2 activities. This is a wonderful way to interact with some of the scientists, including Liz Fletcher, who's one of the wonderful graduate students here, Dr. Noble, which is the scientific director of the McDonald Institute, and Natalie Ouellette, who is a member of the Canadian branch of the James Webb Space Institute. That's perhaps one more slide. Very well, and this is one last outreach thing that was being run at the McDonald Institute. That's the Young Persons Lecture Competition 2019. And this is going to be a number of some of the researchers at Queen's University and abroad who are competing to enter the world stage of a public lecture competition. So that's all I got for you today. Thank you very much.
Thank you, Ben. All right, so our speaker tonight, Nikhil Arora. He's a graduate student here at Queen's University. He's a PhD studying galaxies. He got his start as undergraduate at Jakobs University in Germany and also at the Max Planck Institute. He's a really avid science outreach strange person. In fact, he's one of the organizers for the Astronomy on Tap and sort of the instigator that made the whole thing come here to Kingston. So today he's going to tell you a bit about some of the most energetic things in the universe. I give you a Nick.
Alright, so all of you clap so now I can go home. Is that it? No. Right, so welcome everyone. Thank you, Connor, for that introduction. Today, I decided to talk about energetic events, but give it some sort of a fun flavor. So I wanted to talk about energetic events in the universe that could destroy the Earth. So in that case, CIA, if you're really watching, you're welcome here as well. But yeah, let's move on anyways. So who knows what this is? Yes, Death Star. Well, from the famous film series Star Wars, this is the Death Star. So this is sort of what started the motivation for this talk. The Death Star is this enormous piece of weapon that focuses lasers onto a planet and destroys it. So that just got me wondering, are there things in the universe that could destroy the Earth? Furthermore, very recently, there was something in the news that in April 13, Friday, April 13, so that's quite ominous, 2029, an asteroid in the name of 2004 MN4 is going to pass by Earth, right? So you see this little orange thing over here? That is the closest approach that this asteroid is going to make, and that's about 30,000 kilometers. This is a 320-meter wide asteroid, and it's going to come 30,000 kilometers close to the Earth. Luckily, nothing's going to happen, at least with all the simulations that we had ran. But you still never know. There might be a small possibility. No, I'm just kidding. Anyway, so 30,000 kilometers, for just a reference, is not even enough to go around the Earth once. Okay, so it's going to come really close. So that just got me wondering, hey, what happens if this asteroid actually hits the Earth? What happens if a 320-meter wide space rock actually hits the Earth? Well, so in order to understand that, or in order to actually answer the question how to destroy the Earth, you first have to understand how the Earth was made. Well, we understand that the Earth is held together by a phenomenon called gravity. So we can come together and we can be like 5 billion years ago when the sun and all other planets were created, the Earth was just little specks of dust and rock that came together because of gravity and formed this beautiful planet that we live on. Okay? So, in a way, if I was able to achieve enough energy to reverse this process, I might be able to blow up the Earth. So that's exactly what we're going to do. Gravitational binding energy, as it's defined, is the least amount of energy that you need to break up the object if it's held by gravity. Okay? That's how simple it is. So we're going to try to rack up enough energy to try to break up the Earth into small parts. Okay? Now you might ask, how much is that energy? That's it. Well, that's a lot of zeros, but let's try counting anyways. So that's 1,000, that's 1,000,000, that's 1,000,000,000, that's it. No, I'm tired. So, as it turns out, these are too many zeros, and for physicists, when they see too many zeros, their eyes hurt. So we've come up with a better way to represent large numbers. What we do is we just count up the number of zeros and put them in the superscript. Okay? So that's your crash course into scientific notation. Next thing is, what is this little j doing out here? Well, that is joules, someone said it right. So that is the unit of energy. Now, just to imagine, if I had a baseball and I threw it at you, and you were catching it and not getting hurt, at 100 kilometers an hour, that would require 4 joules of energy. Okay? So just by that, it takes a while. It takes some energy to throw your baseball at 100 kilometers an hour. Just imagine how big the Earth is and how much energy we need to actually blow it up. All right, so now let's go back to the asteroids. What are asteroids? Asteroids are basically just space rocks that are held mainly between Mars and Jupiter. So if we're lucky tonight and it's not cloudy, I think we're going to see Jupiter. No Jupiter tonight. But we should still thank Jupiter a lot because of how big it is. It takes in a lot of asteroids that could have headed Earth's way. But at the same time, every now and then, it'll throw 1 or 2 asteroids our way. So we just have to be careful. We're like frenemies. We hate it, but we also love it. However, depending on how big the asteroid is and how fast it's coming, you really figure out what's going to happen. Now, if you were interested and want to do it at home, there's this really nice website called Solar System Collisions that will let you understand what happens if you throw a piece of rock at a planet. Over here, I've selected Earth. It's a rock. And this is exactly the size, about the size of the asteroid that's coming towards Earth in 2029. It's coming in at 25 kilometers per second. So this is fast, okay? Now what happens when kaboom happens? Well, quite a few things happen. So the amount of energy released over here is about 3,000 megatons. As a reference, all of the nuclear weapons on this planet are about 10,000 megatons. That's about 30% of the energy that is released by this 320 meters of rock. You get a very large earthquake, and you get the crater about 4.7 kilometers. 4.7 kilometers is the start of Princess Street here in Kingston, all the way to the place where it actually turns. That's about 5 kilometers. So you actually get a crater that's about the size of Kingston. Okay? But hey, was that our job? No. 4.7 kilometers craters would actually hurt us. It would be pretty devastating for the continent, but it wouldn't really destroy the Earth. So that's really boring. Okay? So I wanted to push the limits. Okay? So I kept going, and until I found a rock that was about 9,000 kilometers. Okay? That's the size of Russia. Okay? The eastern end of Russia to the western end of Russia is about 9,000 kilometers. Another reference, that's bigger than Mars. Okay? So if a rock came towards us, which is about the size of Russia, or bigger than Mars, well, you'd get an earthquake of 16.9. The crater would be 32,000 kilometers rather. This doesn't really mean anything. I think I broke the code, because what it says is the Earth is shattered into 1,000 tiny pieces, and it's there no more. Well, that's what we wanted, so success. Well, that was the asteroid bit. But now you might wonder, oh, is there anything else in the universe that might blow up the Earth? Well, it turns out the thing that gives us life, the thing that provides life on the planet, can also blow up. What's the closest big engine to us? Well, it's the sun. The sun is pretty much a giant nuclear bomb. Okay? It's performing nuclear fusion, which is bringing in hydrogen atoms to form helium. And while that happens, it releases energy in the form of gamma rays and other types of light. That is done through E equals mc squared, the very famous Einstein equation. As a reference, there are about 10 to the 18 nuclear bombs going off every second in the sun. Okay? So if we count up all the energy of the sun, it would take the sun about a year to blow up the Earth completely. Okay? Just 1 year. Okay? As a reference, 10 to the 18 is the number of ways you can actually solve a Rubik's Cube, a 3x3 Rubik's Cube. So that's what I'm Okay, but the sun is a very teeny tiny ordinary star that we have here. Okay? So it turns out if you take how hot a star is, and you take how bright the star is, well, brightness is directly a proxy of how energetic the star is. The stars form a very beautiful relation, which is called the HR diagram, which was predicted for stars. So here is the sun. Well, there are some bigger, well-known stars. Betelgeuse is in the constellation Orion. It's visible during the winter, very bright. But what's the brightest star that we know of? Well, in order to understand where the brightest star that we know of falls on this particular chart, we have to expand the chart. The brightest star that we know of is called R136A1. Yeah, I know we're great at naming things, but apart from that, this thing is 8 million times more energetic than the sun. Okay? I previously said it's going to take sun a whole year to actually burn through the Earth. Well, this thing, this mammoth beast over here, will burn through the Earth every second. So just think about a 20-minute talk that I'm giving you, and how many Earths are destroyed when I'm talking. Well, stars, once again, when they're at the end of their life, they go through what is called a supernova. Our sun won't do that. Our sun is not big enough. So if a star is about 8 times the mass of the sun, it goes supernova. Our sun is just going to be very anticlimactic. It's just going to go poof. And that's it. But if a star is very massive, it goes supernova, which is more of a bang. Okay? The energy released every second for a supernova is 10 to the 44. That's competing with the total energy output of the sun over its lifetime. It's 10 billion years. That's how powerful a supernova is. So every second, a supernova will blow up 100 billion Earths. Okay, so now we're getting towards the really, really high scales over here. Yeah? Okay, so supernovas happen when your star is at least 8 times bigger than the sun. But what if we make our stars even bigger? What if we make our stars 25 times the size of the sun? Okay? Well, if that happens, well, a supernova occurs nonetheless, but with the supernova comes a very, actually no, that's not it. Here's an example of how bright the supernova is. Sorry. So here's a galaxy, NGC 4526, and here's a picture of the same galaxy with a supernova going off. It's as bright as the galaxy over here, okay? So this actually is very advantageous to the astronomers in the community in the world. Turns out, because supernovas are so bright, they're very, very good objects to measure distances to galaxies. So really, really far away galaxies, the one way we know their distances is through supernovas, okay? Now, as I said, what if we make our star even bigger? If we make our star even bigger, it will go supernova while becoming a black hole. But while doing that, it'll shoot out a really, really intense pulse of gamma rays. Gamma rays are the most energetic electromagnetic radiation that we know of, okay? Now these are called gamma ray bursts. These only last for a few milliseconds to a couple hours. So it depends, the timing really depends on what kind of event is happening. So a couple hours will only happen if a very, very big star goes supernovas and turns into a black hole. Whereas millisecond events happen when neutron stars, and you can ask me about that later, what a neutron star is. Neutron stars collide to form a black hole. That's a very energetic event. Now gamma ray bursts in themselves are 10 times more powerful than the supernova. Okay? So that's looking at a trillion Earths every second. Okay? That's about how many planets there are in our own galaxy. There are about 10 billion to 100 billion stars in the galaxy. That's about an estimate. We can be 10 off by a factor of 10 or something. That's about how many planets there are in our galaxy. This thing will shoot off that many planets. It is said that if a gamma ray burst is pointing straight towards the Earth, it can cause real fatalities. Within the milliseconds, it can pick up 25% of the ozone layers. So it can be pretty devastating. But that's not it. We're not there yet. Now we're going to go to the top of the table. Okay? So who knows what this is? What is it?
A black hole.
A black hole. So recently, well, a few weeks ago actually, we released the first ever image of a black hole. The dark thing over here is the black hole. So it turns out, in order to get the most energetic things, events in the universe, in order to get the brightest things in the universe, you actually have to look at the darkest places. Look at the irony of that. But these shiny things, the bright thing around this black hole, is matter spewing onto the black hole. And because of that, huge amounts of energies are being created over here. Okay? Very huge, large amount of energies. So what happens if we turn the black hole bigger? Okay, this is about 1 billion times our mass of the sun. What happens if we turn up the black hole bigger? What happens if the black hole becomes so big that it's eating so much matter that it's very hard to keep count of? Well, astronomers have a name for an object like that. It's called a quasar. Okay? Quasars are these very, very massive black holes, supermassive black holes, that are eating matter, eating stuff at such a high rate that makes them super bright. That makes them so bright that every second, the power output by a quasar is 100 times a supernova. Okay? How many Earths a quasar can kill? I'm not even going to count for you guys. It's a lot. Okay? So we're not even going to go there. That number is huge. So here's a star that is a couple hundred light years away from us. Okay? This other thing that looks quite like a star, you would think is a star, is a quasar 9.1 billion light years away from us. Okay? Quasars are so bright that they overcome stars. Okay? By the way, as a side plug, this was the 100,000th image taken by the Hubble Space Telescope. So that was good. For a very long time, so quasars actually mean quasi-stellar objects. For a very long time, astronomers did not know what quasars were. Okay, they just appeared very stellar-like, just like a star, but really, really far away. And so once you cover up the quasar part of the image, you see this really, really fuzzy extended object. And that fuzzy extended object is a galaxy. Okay? Quasars are supermassive black holes that live at the center of a galaxy. This galaxy has 100 billion stars. And a quasar is powerful enough to overcome the light from every single star together. That's pretty powerful, right? So I've gone through all of this scale, the energy scales of the universe. Okay, you might ask us, Nick, are we really safe? Is the planet really safe? We've been here for 5 billion years, right? So let's now go through a summary and think about, is our planet really safe? Well, here's everything we've talked about. I'm going to count gamma ray bursts into the supernovas. Well, quasars only happen in very, very massive galaxies. Galaxies like Milky Way, that we live in, galaxies like Andromeda, which is right next to us, cannot really host a quasar. The black hole is not big enough to take in that matter. So we're good there. Supernovae, well, first of all, supernovae happen in very massive stars. But on top of that, they're very rare. In our galaxy, we think that there's one supernova every century. Okay? In the last 1,000 years, there have only been 3 supernovae in the Milky Way galaxy that were observable by the naked eye. Okay? So supernovae are very rare. So we're good there. Our closest, life engine, the sun, is fairly dangerous as well. I might have said that the sun is a measly object, but still pretty dangerous. All the energy, it only takes a year. But the lucky thing is that all of the energy from the sun is not coming straight to us. It's being dissipated in all directions. So we're good there. Asteroids, now that's a big threat, but it would take an asteroid the size of Russia to destroy the Earth. And with the simulations that we have run as scientists, we don't see any event happening like that in the next few 100,000 years. So we're just going to be fine. Well, there's nuclear bombs, but I'm not going to say anything about that. But I'm going to stop right there. Thank you.
All right. Have we got any questions for Nick? We've got a rover with a mic, so there you go.
So just a simple fact, I'm also going to be in the warm room, so if I don't answer all of your questions, I'm going to be up there so you can pick my brain. Yes?
Hi, thank you. I'm curious about black holes.
Okay.
Simply for this fact, do we have any further knowledge other than they consume matter and light?
Any further knowledge?
Yeah.
I think that's pretty significant enough in itself. A supermassive black hole that lives at the center of a galaxy, even though by its mass, it's a very, very small object. It might just make up like 1/1000th of the mass. It's not very massive. But the energies coming from a black hole, as I said, are powerful enough to shut down things like formation of new stars in the whole galaxy. So yes, there's a lot more to black holes than just eating matter. That's pretty devastating as well, but still, yeah.
Just curious where it goes, right? Like,
Well, it comes out as jets. So you see over here, there's a jet coming out. So all the energy that's going into the black hole because of the accretion disk comes out of the jet. Yeah. What happens to the matter once it goes into the black hole? Well, it turns into energy, but we don't know what really happens to it. So, yeah.
okay, thank you.
Yeah.
On your picture of a quasar, was there a jet?
This one?
That one? Like, what's that thing down there?
Well, this thing?
Yeah.
It looks like the M87 black hole, but it's not. So it looks like the same black hole as this one, but it's not the M87 black hole. It's the energy set black hole has a jet on slant to it. So it's an object in the universe. I think it's one of the brightest quasars that we know of. Yeah.
So that the
So yeah, this would be the jet. Yes.
That's the jet. Okay.
Yeah.
I was just wondering, how were you able to determine the differences between the accretion disk and microlensing from behind the black hole?
Oh, so these are things that are predicted. So if you go here, so this is a picture of a black hole once again. So the question is, how are we able to predict as to which part of the disk is actually the accretion disk and which part is behind being lensed by the black hole, right? Okay, so this is something called Doppler beaming, which is things that are coming towards us actually get boosted towards the speed of light, and so they become brighter. And the things that are going away from us, they're actually dimmed. Okay, so this back part is the part which is being lensed by the black hole itself, and the accretion disk is right here. Yes?
Hi. So I was wondering, how do you actually tell the difference between a quasar and a star if they look identical?
That's a very good question. You block it off, and something's left. That's a quasar. That's exactly it. But also, we're good enough that, so you know white light splits into various colors. So we do that with everything in the sky. We take the spectrum, as we call it, the composition of light for every single object in the sky, at least the interesting ones. So the spectra of a quasar looks very different compared to the spectra of a black hole, or a star. So that's how we know that's a quasar and a star. But you can block it off and you see an extended structure. That's a very simple thing. Yes?
How does the black hole work?
Sorry?
How does the black hole work?
How does a black hole work? Black holes are these intense, places in space-time where the gravitational pull that we feel is so hard that not even light can escape it.
How much light are there on each planet?
How much light is there on each planet? We don't know. It's a hopeful question. We don't particularly know how much light there is.
All right, have we got one last question for Nick?
Oh, two people.
Okay, two.
Susan.
Okay, so the jets.
Yes.
I'm fascinated by the jets. Do I understand this properly that the jets from black holes are created because as the matter concentrates to the center, as everything keeps going in, the black hole spins up super fast.
Yes.
And that's why the jets are
Yes,
created.
absolutely. So
Okay.
a little bit is, there's also a magnetic field that's controlling the matter and the energy. So that's what shoots the jets up. Yes, you're right. It's the spinning of the black hole that causes the jets.
All right, any last question? Yep.
Yeah.
How do they get the black hole?
Sorry?
How do they get the black hole image?
Oh, how do they get the black hole image? Well, you should have been here for the last talk. I'm just going to go back, sorry.
Oh yeah.
Well, so what they did was they took, so this is the picture of a black hole. And I'm going to go onto it very, very slowly, and then we can come back at it later if you have more questions. So they had 6 telescopes on the Earth. So they made a telescope the size of the Earth. And the reason why you need that is because farther away the things are, the longer you need to collect light from it. It's like a bucket, okay? So if you want more light, you want to have a bigger bucket. What's the biggest bucket that we know of? Well, the Earth is pretty big, so we'll do that. So we put telescopes across the Earth, and we collected signal from it, and as the Earth kept rotating, it kept collecting more and more signal. And that was how we got part of the image, and the rest of the image we got through computer simulations. That's how we got it.
All right, let's thank Nick again.